All right, I want to take a moment to thank everybody for being here and to thank Lark Widener, who is our secondary science associate with the Office of Standards or Assessment and Standards with the Department of Education. She is going to take us through and help us learn about the new science standards that we're going to implement next school year and be tested over for sixth grade. Thank you, Lark.
Great, thank you so much. Good afternoon, everybody, and thank you for having me with you in the virtual space. Once again, my name is Lark Widener. I'm your secondary science education associate. I came out of the high school science classroom in December of 2021. That's when I joined the department. And I am excited to be here to work with y'all to sort of set the foundational understanding of the 2021 Science Standards document. And so thanks again for having me. So before we start talking about the standards themselves, I just wanted to take a moment and get us thinking about science as a discipline. So if you're in a room with a small group, or if you're not, that is totally fine. Take a moment and think through whether you agree or disagree with each of these statements and be prepared to share why. So statement number one is that scientific ideas are absolute and unchanging. 2, science is a creative process. 3, science is complete. 4, science is a solitary pursuit. 5, science is boring. So take a few moments and decide whether you agree or disagree with each statement and be prepared to share why. I'm going to give one more minute for everybody to think, and like I said, be prepared with your why, and then we're going to discuss as a group. All right, I see some answers coming in the chat, but it'll be easier for me if we can sort of do this with the reactions. So if you are in the meeting, and if you're not in the meeting and you're just sitting in a room with other people, if y'all just want to try to get a group response, that works too. Up at the very top bar, you should see a little smiley face that says react. We're going to use applause for agree and surprised for disagree. So applause for agree and surprised for disagree. So statement 1, scientific ideas are absolute and unchanging. Agree or disagree? All right, we've got a lot of surprised faces for disagree. Is anyone feeling particularly brave and would like to unmute and share why they disagree with that statement?
I will.
Thank you.
When I was in high school, Pluto was still a planet. So scientific ideas are definitely changing.
You stole my favorite example.
That was what I was thinking too.
You stole my favorite example. Yes, I always think about poor little Pluto. Was a planet, not a planet, dwarf planet, right? Has our understanding and ideas around what a planet is versus other celestial objects changed since a certain time frame that I'm not going to explicitly state when I was in elementary school. Absolutely. The other thing I like to point out is I had a genetics professor who said when he was an undergraduate student, he felt like everything he knew about genetics was wrong about every 10 years. When he finished all of his graduate work, He said everything he knew about genetics was wrong every probably 7 to 5 years. Now, as he's heading nearing retirement, he says everything he knows about genetics is wrong about every 2.5 to 3 years. Because as our technology and our ability to test our ideas has become enhanced, our understanding has changed as well. All right, so remember, applause for agree, surprised face for disagree. Agree or disagree, science is a creative process. All right, now I need another brave volunteer to unmute and share their reasoning, because I'm seeing mostly agrees here, why they agree with that statement. I see Miss Altman has raised her hand, maybe. All right. Miss Altman, do you want to unmute and share?
Creative mind to solve a problem?
Creative mind to solve a problem.
Maybe, I would say that.
Okay. Anyone else have a different reason why they agree or maybe disagree? Or do most of our students think of science as a creative process?
Do you want to know if we disagree or agree with that also?
So how would our students maybe respond to this? Do they agree or disagree that science is a creative process?
Oh, I think they would disagree.
Why?
I don't think that they would. I think that they only think about creativity in forms of art.
I see maybe Miss Cantrell. Sorry if I'm mispronouncing anyone's name.
Nope, that's correct. I am at the Rawlings Middle School of the Arts, and our students would definitely say it's creative just because they have that creative minds.
Great, thank you. And I see another hand up, but I'm not sure whose it is. Maybe Chapman?
Yes, I'm over at Alston Middle School, and I impress upon my students, even when we're just having discussions, introducing new topics of the unit, that we speak. One child will have an idea, and then we'll work on that as the others add to that. And they are creating, getting to the main point that we want to. Is the first child stating exactly what we're trying to get to, or are we taking little pieces together from each student and creating to get to the actual fact that we're looking to discuss? So yeah, I'm pressing upon them that they are creating that. It is creative.
Absolutely, thank you. So a lot of people view science as a very dry, sort of regimented subject area, right? You do these steps and you come up with these kinds of things. But really, science is a quite creative process and often requires people looking at the same information and coming up with creative interpretations to that information as well. All right, so remember, applause, agree, surprise face, disagree. Agree or disagree, science is complete. I'm so excited about how engaged y'all are being. Do I have someone who'd like to volunteer and share why they agree or disagree with statement number 3?
I was just going to say that science is never finished. Science is an ongoing process, and the more questions you ask, the more discovery you're going to have, the more answers you'll find. So no, science is never going to be complete.
Thank you. And I think somebody else had unmuted as well.
I did, and that's essentially what I was going to say, just that there's literally thousands of questions that are still unanswered, and so I don't think it will ever be complete.
Thank you. So this makes me think of, and I don't know how much y'all keep up with nerdy science news, but it was probably like 6 to 8 weeks ago. Turns out a piece of the sun broke off and wound up circulating around one of its poles. So if you had the sun breaking off on your doomsday bingo card, you can check that spot. And they actually think it's part of the normal pole switching process the sun undergoes every certain number of years. But it's the first time we've ever been able to observe it, right? So with the new James Webb Telescope, they were able to observe that actually happening in real time. So it's a new piece of information about the interactions in our solar system and our sun. And then number 4, agree or disagree. Science is a solitary pursuit. Anybody want to share their thoughts around statement number 4?
I'll go ahead and share. I mean, we all think of math when we think of science and that they go together, math and science go together, but you need ELA to communicate and you need social studies for the social ethical aspects of science. So I think everything ties in. It's not a solitary discipline.
Great, thank you. If you've ever read a scientific research article, usually how many authors are listed? Is it just one?
No, typically it's a team for sure.
Typically it's a team, right? A whole lab team, or even people from other disciplines of science, or even other content areas like statisticians as well are working on those projects. So scientists don't work in isolation. The final statement, which is a knife in my heart, science is boring. Yeah, so we're all, science teachers. We enjoy teaching science. So I would hope we don't find science boring, although there are parts of science I find very boring. There are certain subject areas that are not my favorite thing. So let's flip it around. How do we think our students sometimes feel about statement number 5? Multiple disagrees. Yes, Ms. Rogers.
If a kid sits in my class and they say science is boring, there is something truly wrong with them.
Great. So I'm happy to hear you have an engaging science classroom. Mixed, right?
We're doing reproductive health right now.
Oh, yeah. That's not boring. And so sometimes it depends on the classroom, right? Sometimes it depends on the subject. I see Chapman, Mr. Chapman.
Well, I was just going to say we did reproductive health last week, and I just couldn't keep. I'd come home every day and tell my wife, "Wow, it's like I'm really teaching. They're so engaged." But it's imagine what the material is that we're discussing.
Yes, absolutely. And then sometimes, it's hard for me to get excited about some of the, really high level physics that I had to do. I'm a squishy science, life science person. I will put myself out there as that. I like things that squish. I don't like things that don't squish. But yeah, so thank y'all so much for sort of engaging in this opportunity to think about science as a discipline. I think this really helps us get in the right mindset of trying to look at the 2021 science standards and the vision that they're trying to achieve. The other thing I like to point out at this point is that one question that I hear a lot of times, or a sentiment I hear a lot of times, is, it feels like the standards change all the time. Well, that's actually legislated. It is legislated that standards are reviewed and potentially revised every 7 years. But when we think about science as a discipline in particular, I think it's particularly important that we review and revise those standards as necessary, because otherwise we might still be teaching Pluto as a planet, right? So as our understanding of science changes, I think it's important that our standards are able to keep up with that changing understanding too. So for today's work, and I come from the world of learning targets, so I like to write my objectives as I can statements. I hope we've all taken a step forward in being able to say I can name and describe the 3 dimensions of science, and that I can explain how the new science standards incorporate all 3 of those dimensions. And so I think Stephanie went ahead and got together for y'all a printed note guide. So I will let you guys know when that is going to be the most helpful for scaffolding, taking notes throughout this session. But first, what are the 3 dimensions? So as identified in the 2012 Framework for K-12 Science Education, the 3 dimensions are science engineering practices, which describe what students do to learn content, disciplinary core ideas, which is what students know, or the traditional science content, and then the cross-cutting concepts, which help describe how students think or how they connect their understanding across different disciplines of science. So those are the 3 dimensions, and we're going to take a deeper dive into each one in the next couple of slides. But overall, practices are what students do, core ideas are what students know, and cross-cutting concepts are how students think about what they know or how they connect ideas. The first page of the note catcher is a really large table. You'll notice each dimension is listed, and then there are 3 blank columns. The first column is something new. So if you learn something new about that dimension, write it down there. The middle column is for like aha moments, like, oh, I already used this dimension in my classroom. I already do these things. And then the last column is for implementation. Is there something about a dimension we talk about today you could try in your classroom before the end of the year? So let's dive into our first dimension, science and engineering practices. So these describe the major practices that scientists and engineers use. It's a total of 8 practices. They're kind of combinations of multiple smaller pieces. It's not a complete list of everything scientists and engineers use, right? But it's like the major things they use in their day-to-day work. These describe what students do to learn content. And it's not just the physical doing of science, it's also the mental gymnastics students use to learn content. I think a lot of us, particularly secondary teachers, we're very good at identifying when students are working like scientists or engineers in terms of labs, right? Like I always felt very strong in that if I had to identify the science engineering practices, I could find them in lab. But this really is trying to move more towards this is what your students are doing all day, every day in your classroom. Scientists do more than just labs. They do more than just collect data. And in fact, the majority of their work is not collecting data. So I have a graduate degree in dairy science. I work with dairy cattle, love playing with cows, definitely my favorite part of my master's program. Not what I spent most of my time doing as a scientist or when I worked in the field as a scientist. So yes, playing with cows, the experiment, collecting data, that's the favorite part. That's everybody's favorite part. That's what gets kids excited. That's what gets them in the door. But it's more than just that. It's the mental gymnastics students also use to learn science. The best news is this is our safe place. This is what's coming with us with the transition from 2014 to 2021. So they were previously incorporated in 2014. They were named and organized a little differently, but the essential parts are all still here as standard 1 and blended with content for performance indicators. So if you remember, 2014 had overarching standard, conceptual understanding with performance indicators underneath it. Those performance indicators where students develop a model of blah, 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 right? So this is our safe place. This is what's coming forward with us no matter what grade or content area we teach. Dimension 2 are the cross-cutting concepts. These are 7 major themes that span across different science disciplines or domains. The ask here is to help students use these as an organizational framework to connect knowledge and connect their understanding. This is our quote unquote newest dimension, and it already exists in your classroom, and it already exists in your instruction. But it might not be clear to students that it's there. These are themes and ideas that we use to organize and think about teaching science inherently as teachers. But students may not realize that. And so the ask here is to help students use these as ways to categorize science into big ideas. My favorite one to do this with is energy and matter. You're welcome to run to the chat and I'll try to read out answers as I see them. You're also welcome to unmute and contribute to the conversation as well. So, can we track energy and matter in living systems? So can we track energy and matter in living systems?
Well, I mean, I just
Oh.
like to say, like in the simplest for 7th grade of the last time I taught this year, you know, the whole, obviously the cycle of cellular respiration photosynthesis. I mean, if that's not tracking energy, I don't know what is.
And matter, right? Yeah, so we can
Exactly.
track them in cells, for example, with respiration and photosynthesis. Are there any other larger scale ways we track energy and matter in living systems?
Again, the human body system, digestive. The entire
Digestive system,
Yeah.
yep. And then what about ecosystem interactions? So food web, pyramids, trophic levels.
That's the
Those all
easiest.
track.
That's the easiest one for them to get.
Yes, absolutely. Do we track energy and matter in non-living systems? Come on, where are my 6th grade teachers at?
We do. I'm not a 6th grade teacher, but we do.
Okay, do you have
Energy,
an example?
yeah. Thinking of some of the activities that they've done with, you know, temperature. I know that they've done some of those things. Trying to
Cars,
think of some of the cars. Yes, you know,
solar energy.
yeah,
Potential energy.
yeah, kinetic.
How about an Earth system where we might track energy and matter? It's a big cycle. Weather, the water cycle,
The
right?
water cycles.
Yep. How about my 8th grade teachers?
Rock cycle.
The rock
Even
cycle.
the rock cycle, even the rock cycle is matter.
Yep, and it's energy too, because there are energy inputs into those systems, right? Do we track energy and matter in designed systems? So things humans have made to solve a problem. How do most of y'all get around town?
Hybrid car.
A hybrid car? Yep. So
Airplanes.
airplanes, can we track energy and matter through those designed systems?
Yes, the car tracks it for you.
If your car's got a good enough computer, it tracks it for you, for sure. So are there overarching rules about energy and matter that we can name and identify? That apply everywhere we've been in the universe so far?
Law of conservation of matter.
Law of conservation of matter. Energy have a counterpart. Yeah, so could we all agree that energy and matter is a big idea in science? No matter what specific domain or discipline, whether it's life science, physical science, earth science, it's a big idea. Does it give students a starting place to think about something new? If they can step back and go, what do I know about energy and matter? What rules, what relationships do I understand? That's what these are. It's a toolbox for students to use when faced with something new. So another example I like to bring up is in 6th grade, there's a performance expectation about waves, and it's primarily about the structure of waves and sort of how waves work. And so let's say you've been teaching about waves, and you've been using electromagnetic waves as your example. And we're just purely still at the level of like, trough, crest, all those parts of a wave. But maybe your assessment is waves on a beach. How many students would go, I don't know anything about the ocean. You didn't tell me about the ocean. I can't answer this question. We haven't learned about the ocean or waves in the ocean yet. Right? I had students who would do that. But if we can help students learn to take a step back and think a wave is a wave and has the behavior of a wave, no matter what kind of wave it is, that gives them a starting point then to attack that new situation and develop an explanation for it. I keep calling these the quote unquote new part because they were not explicitly part of the 2014 standards. They weren't called out the way they are in our current and in the 2021 standards. They were identified in the front matter of that standards document. But who reads the front matter? What do most of us do when we open up the standards? All right, I just got to get to my grade level. I just got to scroll down and get to my grade. They were also identified in supporting resources. But they were there. They just weren't called out as directly as they are for 2021. And the cross-cutting concepts exist in your classroom instruction already. They come through in the way you question students, the way you probe their understanding, and in the way they talk about what they're learning. They exist. The ask is just to shine a light on them and bring them forward for students to enhance their understanding. The final dimension, dimension 3, are the disciplinary core ideas. These are domains that have broad importance across multiple science and engineering disciplines. At the department, we often refer to them as our content nuggets. They are physical science, life science, earth and space science, and engineering technology and applications of science, or ETS. That's where part of that standard 1B from 2014 came to live as a content area, as engineering technology and applications of science. As a side note, ETS never stands alone. You don't have any performance expectations that are just engineering. It's always housed underneath other content. So it's always tied to physical science, life science, or earth and space science content. For example, students might be asked to develop a device to minimize or maximize heat transfer. That is physical science content with an engineering tilt or lean to it. So that's where you're going to see this one live. This is also where we had the greatest amount of shift, and in middle school had the biggest shift of any grade band by far. On average, somewhere between 60 and 70% of your content is new to your grade in middle school. It is less so in high school, about the same to maybe a little bit less in elementary school, but they still have shifts within their grade bands as well. But just know, and I like to address that elephant in the room, that for middle school, roughly 70% of your content is new. And unless you looped with students before, it may be content you've never taught before. Part of that was to try to make those middle school science courses more truly integrated science courses and move away from that sort of traditional progression of physical science, life science, earth science as students move through middle school, and try to meet that integrated science goal. So before I move on to talking about sort of how the standards are organized, do I have any questions about the 3 dimensions, the SEPs, CCCs, or DCIs? Because, you know, education loves an acronym. Great. So before we jump into the coding system and what the performance expectations look like, I do want to make a note about how they are organized. K through 8, our standards are organized by grade level. And then in 9-12, the high school grade band, they break out into content areas, because traditionally we teach high school in different contents. If you've looked at the 2021 science standards, you may have noticed they look very similar to another set of 3-dimensional science standards, the NGSS. It's important to note that we are not a direct adoption state, so we did not take the NGSS, the Next Generation Science Standards, and say, these are our standards. We are what we call a framework aligned state. So we have 3-dimensional standards grounded in the framework, but we do not exactly match the NGSS. What that means is there are edits, there is some reorganization, we kicked some PEs out, we added some of our own. One of the biggest things that happened is the NGSS is a middle school grade band, but in South Carolina, we teach per grade. So one of the first things to always check for middle school teachers is this content in my grade? If you're looking at other resources for other 3-dimensional science standards like the NGSS, and they've been around for 10 years, they just celebrated their 10-year anniversary, there's a lot out there for them. First thing to always check, is this in my grade? Because those are going to be a grade band set of standards, whereas we are individual grades. Same thing is true for high school. They're going to go by content area, not just a general high school grade band. So first thing to always check, is this in my grade? Because we have 6, 7, and 8. And you're going to do that by looking at the coding. I just want to make a marked change in language here, and I would like y'all to hold me accountable for it. When referring to the document, I call it the standards document. However, these are not traditional standards, they are performance expectations. They are 3-dimensional statements of what students should know and be able to do by the end of instruction. They are end of instruction goals. They are not objectives for a lesson or instructional strategies. A performance expectation is the 3-dimensional statement you see at the top of the card. So for this example, we're looking at 7LS23, develop a model to describe the cycling of matter and flow of energy among living and non-living parts of an ecosystem. In the blue italicized text, you will find our science and engineering practice, develop and use a model to describe a phenomenon. Every performance expectation starts with practice. They all start with what are students doing. How the DCI and the CCC come in depends on what makes the most sense for structure of the sentence. But know that every PE starts with practice. Our cross-cutting concept in the green bold text is the idea that energy and matter can be tracked as they flow through a natural system. And our disciplinary core idea or content in the orange underlined text is that energy and matter cycle through the living and non-living parts of ecosystems. I'm starting here with the PE, and then those 3 boxes at the bottom are what we call foundation boxes, because those are on every single card. There's some other features that may or may not be on the card, but we're starting here with the statement, which is the performance expectation, and then the foundation boxes sort of describe what are we looking for in that practice, what are we looking for in that cross-cutting concept, what are we looking for this content. So this is like that second page of the note catcher where you can fill in. These are summaries of, it's not what the whole box says, it's just summaries within those foundation boxes. How are they labeled or coded? So the first letter or number you see is the grade or content area. So here we're in grade 7. The next set of letters are going to tell you the domain. So life science, physical science, or earth and space science. Remember that ETS never stands alone. It's always tied to other content. The number with those 2 letters is going to tell you the core idea. So this is life science core idea number 2, which is ecosystems, interactions, energy, and dynamics. The final number is the standard number. And this is another place where things get a little tricky for middle and high school. The standard number goes with the domain core idea, not the grade or content area. This is the 3rd standard number of LS2 for middle school, not necessarily the 3rd standard for 7th grade. I'd like to note that because every once in a while I get a panicked email saying, oh my gosh, I'm missing a standard, because it might go LS21, 22, 23, skip 24, and then go to 25. That is because that standard number, that performance expectation, is in a different grade in middle school. So you may not have all the numbers in sequential order for the standard numbers, and that's okay. You're not missing a page. You didn't download the document. Everything you need for your grade level science courses is in the document. It's just that the standard number goes with the domain core idea, not necessarily the grade or content area. So I'm sure that's about as clear as mud. The big message is you're not missing anything. The other thing that means too, it's important to note, is that they are not sequenced for instruction. You do not have to teach the first one on the first day. You are welcome to put them together in different ways to try to make different instructional experiences for your students. You're welcome to start in a totally different order, or whatever your district has determined is the sequencing for your district. But no one is saying you have to do the first standard on the first day or the first PE on the first day. So another thing to check for middle school is this core idea standard number in my grade? Because you may not have all of them. All right, so for this next portion, I like to go to the actual standards document. So I'm going to change how I'm sharing my screen and go to the standards document. One of the first things that's not a huge deal, but is kind of nice, is that the table of contents is clickable. So what, oh, I see I have a hand up. We good? Great. So somebody let me know a grade. Y'all want to go to 6, 7, or 8?
6.
Okay, we're going to click, and it's going to take you straight to the first page of 6th grade. No matter what grade you teach, this is what your first page is going to look like. On the top is just some exposition about 3 dimensions. The inquiry questions are there simply as examples or starting points. They are not required to be used. You don't have to use them, but you're welcome to use them as a starting point idea of how might I start thinking about putting these pieces together for students. To me, the most important thing on this page is the statement underneath about bundling of performance expectations. If you try to teach these one at a time in a sequential order, you will not finish in time for the end of the year. A lot of them overlap with one another. And there are also ways to put them together uniquely as well. Bundling means you're usually teaching more than one performance expectation at a time. So for example, we have waves, and then how objects are perceived by the eye, and then how the brain interprets information in 6th grade. That's a bundle right there of 2 physical science plus 1 life science performance expectation. Those guys overlap with one another in terms of content and understanding needed, so you might teach them all together. That's what they mean when they say bundling of performance expectations. I'm trying to find one that fits on a page. Oh, perfect. So this is what the actual performance expectation card looks like itself. The gray box at the top tells you what your domain core idea is. So here we're in PS1, matter and its interactions. You can see the performance expectation statement with the code and those 3 foundation boxes for the SEP, the DCI, and the CCC. There are 2 more pieces of information that can be on a PE card, but might not be there every time. The first is the clarification statement, which just gives you a general idea of directions to take, starting points, not at all intended to be limiting in your classroom. The second you'll see is the state assessment boundary. We at the State Department are bound by the state assessment boundary. We cannot cross it. Are you necessarily bound by the state assessment boundary in your classroom? And that's an open question. You're welcome to unmute or say in the chat. Are you necessarily bound by the state assessment boundary in your classroom?
I wouldn't think so. You could take it further if you had time or the kids were ready for it.
Absolutely. So sometimes you have to take it further because it helps build the understanding, and then you know they can meet the state assessment boundary. Sometimes the state assessment boundary is super helpful. Like for example, there's in biology, they don't have to do Hardy-Weinberg equilibrium anymore. So, which is a pretty high level stats concept, and we don't have to do any chi-square or anything. If I know that about 9th graders, I don't have to do it. But sometimes they're a little contradictory. So for example, there's a 4th grade performance expectation about light entering the eye and objects being seen, but it says Roy G. Biv is out. Are 4th graders going to ask, why are all these things colors? Are 4th graders likely to ask that question when learning about the eye and electromagnetic waves or the light spectrum? Absolutely, I think 4th graders are going to ask, why are these things colors? Right? Don't feel like you ever have to say to a student, oh no, that's beyond the state assessment boundary, we can't go there. Would students accept that as an answer to their question or their wonder? Saying, oh, well, that's beyond the state assessment boundary. Sorry, Matthew, go ahead.
I mean, I hope not. And I would think a lot of things you can take further. Even now we have where it's like not tested material, but a lot of times it's stuff that we still go over because it enhances what they're learning.
Absolutely. If you need to go there in your classroom, you go there in your classroom, right? So don't feel like the state assessment boundary is telling you you can't do things. It's telling the State Department and our item writers, you can't do things. But as a teacher, you have the flexibility, you are encouraged to do what you need to do to meet your students' needs. And if that's going beyond the state assessment boundary, then that's what needs to happen. But I'd like to point that out because some people think it's supposed to be a limit, and it's not intended to be a limit in classroom instruction or classroom assessment. But sometimes they are helpful to think about, you know, we all have content that we really like and we like to plan. We have to go, I'm going to teach them all this cool stuff. So it is helpful to think, is this really foundational to their understanding of this concept, or is it something that I like to do? So do use it to ask yourself those questions. But if you need to go beyond it to get your kids to understand the concept, then that's what we do in our classroom because that's what teachers do best. The final thing at the bottom are links to the framework. I'm just going to click and open one just so I can show y'all. You do not need to pay for the framework. I have a bounded copy and I always work in the online version anyway. You can download the free PDF if you want the PDF. You can order it if you want. I always just click the X and say, no, thank you, if I want to look in the framework. Those links will take you directly to the page related to whatever's stated in that foundation box. So that science engineering practice, that disciplinary core idea, or that cross-cutting concept. All right, so any questions or clarification about the performance expectation cards themselves?
I posted in the chat, but I was just curious if there's anywhere that kind of says what you may want to bundle or if teachers are kind of expected to make those connections.
Thank you for bringing that back. I was trying to scroll back and look through questions as well. So your instructional materials are already bundled. So that's the first thing to look at. Is all of the materials for 8th grade or for middle school were bundled already. I am about working smarter and not harder. So I would look and see what bundles exist for other 3-dimensional science standards as well as a starting point. But just know to look out for states and other groups who use the middle school grade band as opposed to grades. Some of those bundles might have something extra or might have a PE that's not actually in your grade included. But those would be my 2 starting points are what your instruction materials are bundled like, and then there's a couple different 3-dimensional bundles out there for middle school as well.
Thank you.
Mm-hmm. Yeah, and so I think Stephanie also answered the pacing. Pacing and all of that curriculum is a local control decision. We don't do that at the State Department. That falls under local control. Yes, Mr. Chapman. So the goal here is that all three dimensions purposely articulate across the K-12 continuum. That's part of the reason for the shakeup in middle school, is to make those more integrated science courses that articulate across K-12. There should be an increase in depth and or sophistication as students matriculate from kindergarten to the 12th grade high school endpoint descriptors. And the vision is that students explore content by engaging with practices and using the CCCs to connect their understanding, to deepen their understanding across all science domains. That we help students build a scientifically based worldview as they leave 12th grade, as they graduate from high school. And so for a quick clarity and closure, if y'all would head to the chat, we're going to do a waterfall protocol. What that means is you can type, but don't hit enter until I say waterfall, but you can start typing, just don't hit enter yet. And share something about a dimension, either something new about that dimension, a way you realized or you already use that dimension in your classroom, or a way you could try it before the end of this school year. I'll probably give you about 30, 45 seconds to type. And waterfall. So thank y'all so much for your time this afternoon. I really appreciate the opportunity to work with you guys and get you guys sort of the foundation laid for the 2021 science standards. If you wouldn't mind taking this quick post-assessment for me, if you're sitting in a room with multiple people, you can scan the QR code with a phone, and I'm also going to add the link to the chat. That should open up the form for you. And while y'all are doing that, I'm going to go through and read what some of you guys wrote for our clarity and closure. That somebody said they didn't realize they were already doing the cross-cutting concepts through questioning, using the cross-cutting concepts to help make connections about what they've already learned. Content nuggets as the DCIs. SEPs tell us the do's. Already feel comfortable with the dimension 1, the SEPs. using creativity to explain technical concepts, integrating SEPs regularly through data analysis and activities. Performance expectation is not an objective for a lesson. Thinking about energy and how to include more hands-on activities for students. Just in case it moved too far up, I'm adding the post-assessment link to the chat. Once again, thank you all so much for your time this afternoon. I enjoyed the opportunity to work and discuss and think about science with you guys. This is mine and my elementary colleague Brent White's contact information. Just as a heads up, email is always better than a phone call. I'm usually out working with teachers, and so more often than not, you're going to get my voicemail that's going to ask you to send me an email anyway. So thank you so much for your time and for filling out my post-assessment, my post-survey, and I will hand it back off to Stephanie.
Thank you, Lark, and thank you everybody that came. I am putting in the chat right now the PL section number. If you have not had a chance to register, please make sure that you take a moment and pop into PL and get that registration done for us. And as Kelly stated earlier, if you have anyone that was in your room and was having tech issues and couldn't log in, if you could make sure that they that their name shows up somewhere in the chat for us so that we know where they're supposed to be. And with that being said, thank you all. Have a wonderful day. Thank you, Lark.
Thank you, and I'm happy to linger and listen as people finish up and check out if there are any additional questions or clarifications for anybody. Oh, and don't forget to end the recording.